session will focus about not only water management, not only water treatment, but about, okay, we are going to consider water as a raw material itself. And so we will focus on how we can recover some interesting raw materials and resources from water, different waste streams, even energy transformation of waste into biomethane or hydrogen, etc. So this is a first approach to the webinar. Short introduction, and I'm going to give the floor to the first speaker, that is Victor Herraiz from ITEX, that is going to present the maybe the approach to the project and the first maybe the first results we are obtaining in this project in Life Anhidra. So Victor.
Thank you, Oscar, for the presentation. I will try to share my screen now. Yeah, I think you can see my screen right now.
It's okay.
Okay, so thank you, Oscar, for the presentation, and I'm in charge to break the ice with this webinar that is Life Anhidra is hosting. So I will explain what is Life Anhidra, how are we overcoming the problematic that Oscar explained after about the water scarcity we're suffering in the UE. And Life Anhidra is a system that is used for producing garments, but without any water discharge. How are we doing that? This is the consortium that we have established. You can see it's a very small consortium, but this makes sense. Later you will see why. We have Pizarro from Portugal. It's near Oporto in Guimarães, and it's a textile finishing company with very international brands and lots of production of denim garments, and they have very almost any finishing process that you may need for a garment. Genologia, it's a company based in Valencia, in Spain, and they develop sustainable and eco-efficient technology for the textile industry. And last, ITEX, where I come from, it's the Research Textile Institute, and we have like a pair of laboratories that can do all of the essays that are needed for the textile industry, also certificates. But we also have an R&D department that do projects about the textile industry. So going back for the first partner, it's Pizarro. As I say, it's a textile finishing company. They do laundry, they do dyeing, they do finishing, and they do printing of garments. And their main product is the denim. And you may know that denim it's one of the most used products, one of the most consumed garments, but it has a quite different manufacturing process than other garments. In this case, for acquiring this look that is characteristic of denim, is this distressed look, you need many different processes. You can see the stone washing, enzyme washing. This what it's what they want to achieve is like this vintage look that usually denim or jeans have. For this process, they're usually very environmentally concerning. Here you can see the sandblasting, for example. It's very dangerous for the people that is working. Stone washing is also very environmental polluting. So it's clear that we have a problematic in the textile industry. In the first place, the water scarcity that Oscar talked before, 11% of the UA it's affected by this problem, and it's expected to even grow more for 2030. And especially in the south of the EU, it's especially concerning because here the water bodies are less, and they're also non drinking. So the water scarcity here is very concerning. Also, we have that the textile industry is one of the most water consuming industries. It represents 4% of the global consumption of water, which is many. And in the EU, we have 30% of production of textile. So it requires a lot of water in this region. Lastly, the aquatic pollution. The textile industry is also very chemically intensive, so a lot of these chemicals ends up in the wastewater stream, and they're not eliminated in the wastewater treatment plants. For example, I'm sure you've heard about the microplastics or microfibers or even fluorocarbon substances. They're all very persistent in the environment and they cannot be eliminated. So how is Life Anhidra trying to overcome these environmental problems? This system is a water regeneration loop that in the plant that it's installed, it can reconditionate the water for use again in these processes. So for an estimation of the results that we want to obtain in this project, it will be a reducing of water inlet by 92%, water discharge avoidance of 98%. And you might think that we are installing a new system, maybe the energy will be more, but we've estimated that the energy you need to send all of this wastewater to the wastewater treatment plant can be implemented in this system. So it will also implement an energy saving of 50%. So what we try to achieve with this project is the reduction of textile industry water consumption, the water reuse, so less water is in, but less water is out also, avoiding discharges. Also, here in this process, we will have a waste that in the frame of circular economy, we need to reintroduce in the industry. And also for this project, the operational good practices that need to be implemented in the factory. So we have a very successful project. So this is the project, the system of Anhydra is using. First is the laundry rotatories that are washing the denim. First, we have a pre-filter mechanical filtration, then an ozone treatment with an ozone generation that puts in contact with the water. Then we have the ultrafiltration treatment or gills that it's the final part of the treatment. And then we have a buffer tank that gets all of the water so it can be available for when the production needs this fresh water. So you see it's a closed circle that it can be working in this closed manner for about 30 days, we're estimating. Here you can see a bit in depth the parts of the system. First, we have the mechanical filtration, where we eliminate most of the solids and the turbidity of the water. Then we have the ozone treatment in those autoclaves. We put the water in contact with ozone that we reduce the color of the water and also the solids. What we do is here, since we're using denim, we are oxidizing the indigo molecule, so it becomes non-blue, so the color is reduced. And lastly, the ultrafiltration treatment, what we do is use membranes to filter the water to have a very high quality water for use again in the laundry system. Here you can see a bit better how the water goes from this blue that is characteristic of the indigo dye stuff to a much clearer water that can be reused in the system. And one of the main targets we have in this project is how we can reduce all of these waste that we are acquiring from this system. Mainly, this waste is made up of cellulose fibers that are removed from the garments in the laundry system because the enzymes are degraded in the cellulose or the stones are in friction with the garment. Then we have this sort of paste that we aim to reduce to put again in garments or any parts of the industry. So the first thing we've done with this residue is to reduce its size so it can be used in a pigment-like process. So we've tried two processes: a dry process, which can reduce the particle size up to 55%, and a wet process that can reduce the particle size to 98%. So for the wet process, you also need a drying operation that can be done in a spray drying machine. And here you can see the fiber, a SIM image of the fiber we're acquiring from the system. And this would be the size reduction in a dry process in a stir ball mill. And this would be the wet process, but with the dry spray dry reduction. You can see we achieve a small particle size that can be used. We've tried two methods: the pigment dyeing, which is use this pigment in exhaust process in a bath that can dye fabrics with these thread looks that can be very interesting for the industry. And we also done a quilting process that we've prepared a printing paste with this pigment, and we apply it to fabrics as in a printing process. Other method that we've tried to implement this waste again is to use it for methane generation. We've done a preliminary study with a very diluted sample, and we've see that this waste doesn't stop the growth from the microorganisms. So we think if we use a much more concentrated solution, we get a much more higher methane generation. Another considered routes for this waste, it's like the most typical ones for this kind of residues, is to use it with hot plate, but you need a thermoplastic fiber. You can use it in a wet laid technology, like in a paper-like system. For composites, you can put them as a reinforcement in a matrix. And also you can obtain cellulose-based yarn as viscose or tencel, lyocell, those kind of new yarns. And that be all. Thank you all for your attention. Here you have the website and my email if you want to ask any doubt. Thank you so much.
So thank you, Victor, for your interesting presentation. You've seen how the industry is facing the water problems and which are some of the solutions the textile industry is suggesting to reuse water and to reduce the consumption of water. So in the same way, the next speaker, next project is going to present also some solutions for the textile industry. Our next speaker is Rick Horseboom from the Water Footprint Network that is going to present the REWAFT project. So please, Rick, the floor is yours.
Yes, thank you so much, Oscar. Am I audible?
I don't know. We cannot hear you.
You cannot hear me?
No, I can hear you.
Yes, loud and clear.
Okay, so some can hear me, some cannot hear me. That's curious. Test, Oscar.
Rick, I think we cannot still. Okay, the people is hearing them. Okay.
Well, if only 3 or 4 people can hear me, then maybe it is still on my part. But that's curious. Shall I share my screen, or are you sharing my presentation? Oh yeah, if you cannot
he
hear,
doesn't hear you, so
if he cannot hear me, then that's an interesting one. You know what? I'll just share my own screen. I think that should work. Let me see. Okay, I think for the people who can hear me, you can see my presentation screen now, right?
yes.
Yes, wonderful. Okay, well then I guess I better just get started, and hopefully Oscar can get his audio to work. Yeah, thanks, Oscar, for having me on the webinar. My name is Rick Hogeboom. I'm executive director to the Water Footprint Network, based out of the Netherlands. I'm also affiliated to the University of Twente, where I hold an academic role. So I'll get to that a bit in a minute, and I'll quickly take a few minutes to present our project called REWAFT, helping the textile industry reduce its water footprint. At a glance, our project, I saw most of the projects in the list are LIFE projects. We are an Erasmus Plus funded project, specifically in the funding stream on partnerships for higher education. As you may know, Erasmus has a number of funding schemes. This one is about partnerships. And the objective of our project is also where our very interesting acronym, of course, stems from, is reducing the water footprint of the textiles industry, or REWAFT for short. Erasmus projects are short projects, only 2 years, and we're over, 60-70% in, so it's a few more months and then we should conclude the project. We have partners from 4 countries, Lithuania, Spain, Greece, and the Netherlands. It's coordinated and led by Kaunas University of Technology in Lithuania. And we, as Water Footprint Network, represent the Dutch partner. You can see the logos of our other partners here. We have IDEC and West Ethica University from Greece. And we have UPV from Spain, and Latia is also a branch organization for textile producing companies in Lithuania for the connection to actual practice. Because there are, first maybe one slide, a few words on the Water Footprint Network. For those of you who do not know us, we are an NGO, a non-profit knowledge center based out of the Netherlands. Our mission is to promote fair and smart use of water worldwide. So we have a global scope, not just Dutch, not just EU, and that's probably good because we actually are experiencing the wettest year on record so far here in the Netherlands. And you can maybe also hear I'm still recovering from a cold, which is, given the temperatures and the water here in the Netherlands, not surprising, but for it almost being summer, it is. Although I understood that also in Alcoy you had your excess of water, so it's very timely that we're talking about water shortages and water footprints here. But well, let's overlook that for a moment. It's based, all the things that we do circle around this water footprint concept, and that was developed some 25 years ago here at the University of Twente, where I'm still affiliated as a professor part-time. And it really found its way into policy and practice because companies also found an interest in understanding how dependent they are on water resources and also what impact they have on water resources. And we try to achieve our mission through a number of core activities. Clearly, we are a network. We try to stimulate exchange. We provide trainings. But more importantly, perhaps even, is data and dissemination. So we try to collate all kinds of information, metrics, publications around this water footprint concept and put it in our database. We also maintain the global calculation standard on water footprint assessment so that we all calculate by the same rules, so to say. So when we talk about what is a water footprint, what constitutes water use, we have the calculation rules to do so. And furthermore, I mentioned the global scope. So we are part of the international water stewardship arena, if you will. Maybe you are familiar with the science-based targets. One of them is on water. It's just launched earlier this year. That's one of the targets that we have developed for the science-based targets. But for instance, we also work with the CDP to develop their water questionnaires that are sent out to many companies worldwide to help them report on all kinds of sustainability topics and themes. But enough about WFN. Back to the project. We have a number of core outputs or deliverables, if you will. And as you may know, Erasmus is about education, right? So there's a lot of focus on training and education. First, we have an in-person series of seminars that we have developed on how to reduce the water footprint in textiles, but it's mostly geared towards students, right? So all of our higher education partners in Spain, at UPV, in Lithuania, in Greece, are teaching this seminar series that we have developed to higher education students. We did try in all of the products to really get the link between the universities and the scientific knowledge that there is and the practical application by industry. And for instance, that meant that we had an industry working group to help us develop these seminars for the students over the course of the project. But the main audience were students. On the other side, we also have an online self-paced e-learning course that we have developed. But this one targets mostly industry professionals. So you can see it as vocational training. How can people who work in the textiles industry improve the water footprint of their operations? And that's a self-paced e-course that we have developed for this. And with this information, they can, of course, build the capacity within the organization, but also hopefully that helps them develop their corporate water strategies when it comes to water. And for some of them, and I will touch on that later, we also work with a number of companies to develop action plans to really see some concrete output and improvement as part of this REWAFT project. Then there are various dissemination activities and awareness raising campaigns more broadly, and that's also why most of the team is currently at the Outex conference, which is quite a big deal in the textiles discipline. There's one bigger output that I will spend a little bit more time on talking, because that's the one that we were responsible for most strongly within the REWAFT project, and that is that we have developed a water footprint of textiles calculator, and that is basically an online interactive web application where that is featured both in the seminar series and in the e-course. So it can target both students and professionals in the industry itself to really help understand what the water footprint of a particular operations is and derive from that how they can reduce it. The tool is based on the methodology that we have laid out in the water footprint assessment manual, and hopefully it then also informs these corporate water strategies of the users of the tool. So I thought it was a bit dangerous to give a live demo with all the technicalities, so I just made a few print screens to talk you quickly through what it can do, just to give you a glance. So we have it hosted on the project webpage. I have some details later on. But basically we ask somewhere between 15 and 20 questions, depending on what you select within the tool. We try to guide you through talking mostly now from the perspective of a company that is active in the textiles industry, on what kind of company you are and what you already know about your water consumption, about your water pollution, about your water footprint at large. So first, for instance, we characterize what kind of company do we have, what kind of activities take place, from spinning to weaving to knitting to finishing, or all of them. But also what kind of materials do you process, because there's big differences between, for instance, whether you produce things made of cotton or of wool or of polyester, synthetic fiber. So we try to differentiate according to the type of fiber. And I think most, well, innovatively, if I can say so, there are a number of tools, not that many. There are some tools that help you calculate all kinds of sustainability dimensions of textiles, including water to some degree, but especially to get it at the level of different processes within the textiles, particularly wet processing steps, that is really not there yet. And that's where we put quite a bit of emphasis on or effort into to get also information at the level of the process step. So that would be on the desizing, on the scouring, on the bleaching, on the mercerizing, etc. And you can then select as a user, as a company, what applies to you. Now, the challenge that we always have with these tools is that water is quite complex and dynamic, and you need a lot of data on that as a company to really know very well all the dimensions of water that you might be impacting or be impacted by. And that is often then infeasible if we want to know all data and all information, since it's simply not there. But it also should not be too simplistic. So here we really try to balance this availability of data and the complexity of water with where we think the industry might be at the moment. So for instance, you can enter your, if you know the water consumption at the process level, you can do it in the tool. You can enter that information. But if you don't, then we will have under the hood, we have default values for which we can give you a guess of where it might be, so that it accommodates different levels of companies in terms of how ready they are in their how advanced they are on their water stewardship journey. That for water use and for water consumption, differentiate between the water you use but then return back to the system and the water you actually take out of the system that doesn't go back to the water system. And we also do that for the pollution side, so what we call the gray water footprint. So what would be the different contaminants that might be in your effluent? There's a whole bunch of effluent or contaminants, pollutants that you can enter information for. For the sake of time, I won't go into that in too much detail. But basically, you go through this list. If you have the information, great, you can enter it. If you do not have the information, then we have some data under the hood to provide that for you. Well, if you have answered all the questions, depending on the settings that you chose, you will get some results. You will be taken to the results page. And the results page will look very different depending on, of course, what you have entered for your company. In this case, I only entered a cellulosic fiber producing company, but with various processing steps within the organization. So it will tell you in your graphs your water use, your blue water footprint for each of the steps. It will also aggregate that to the different fiber types, which might be relevant if you have multiple fiber types entered. And it will tell you something on your gray water footprint, which in this case I didn't fill out in an awful lot of detail. So it will just give you one default number that we found. I think what is more interesting perhaps than even the direct numbers is that we also try to think of how can we take it one step further, and that is to come up with to also present the implications of such a footprint. So how bad is it? So what? How should we interpret it? How can we compare it? And there we basically within water footprint assessment have two checks. The first is, are we efficient enough? So are we not exceeding what is a plausible amount of water for a particular process step or for a particular operations even? And the other one is, does it take place in an area that is affected by water scarcity? So this first efficiency check we do by comparing your actual water footprint to a benchmark for that water footprint. So here, for instance, and again, this is a hypothetical example, but we entered the actual water consumption for the different processing steps that this company has and compare it to a benchmark that we took from literature for that step. And then we can see, for instance, that with these numbers, for some steps, the company is efficient enough. And for others, there are improvement. Those in the red, there's room for improvement on those steps compared to the industry standard. Ideally, we also have the scarcity check, but for that you would need a lot of geospatial information on the production locations of the companies, and that was at this moment one step too far for the tool. So there we will take you to other tools where you can continue your assessment, for instance the science-based targets tool that I discussed earlier, but also our other water footprint assessment tools that we have within the network. So that's a link through to make it even more complete. It will show you the results on the website, but you can also download your PDF with the results, of course. And that is in a glance what the tool is about. So if you want to try it for yourself, it shouldn't take too much time, either for your company or for just to play around. If you scan the code, it will take you directly to the calculator itself. And here you also see some contacts for the project, for our network. And if you want to reach out to me, then you have my info here as well. So thank you for that. Hopefully you can hear me by now, Oscar, and in that case, back to you.
Yeah, for sure.
Okay.
Thank you very much, Rick.
Yeah.
So thank you very much for your presentation, and also I invite you all the audience to visit the website of the project, because there is not only available this kind of tool, but also an open course about textile industry engineering and water, and how the water can be managed in the industry. So interesting, and also waiting in LIFE ANHIDRA to attend the final conference of REWAFT in Spain. We have already been invited by the university.
Very good. Very good.
This event will be in September of this year, and we are very, very happy to attend. So thank you, Rick.
Thanks.
So for the next speaker, next project, we are going to present a sister project of LIFE ANHIDRA, which is LIFE Recyclo, that is focused on the reuse of water, not coming from industrial textile processes, but from laundry processes that are very close to also to this kind of processes, but maybe at smaller scale. The presentation will be released by Lisa Rubier from Treewater. I think it's already here in the screen. So Lisa, the floor is yours, please.
Can you see my screen?
Yeah, you will see your screen, yeah.
Okay.
Okay, now it's in full screen, thank you.
It's in full screen, okay, perfect. So hello everyone, and thank you for the invitation. I'm very happy to be here today to present you our LIFE Recyclo project, which is about the reuse and the of laundry wastewater. So this LIFE project is supported by the company Treewater, of which I'm a member. The company was founded in 2017 and currently employs 15 people. So we provide treatment and recycling facilities for industrial wastewater, and we are specialized in advanced oxidation technology, which is the main module in the LIFE Recyclo project. So the LIFE Recyclo project started in 2021 and will finish in 2026 after 4.5 years. The project was due to finish in February 2024, but we have obtained a 2-year extension. And the budget for this project is almost €1,005,000. So the laundry industry covers a number of sectors, including hospitals, hotels, and private laundry. On average, 4 to 21 liters of water are needed per kilogram of linen. So this wide range is due to the type of washing machine used. Either it's washing tunnels for very large quantity of linen, which are very water efficient, or washer extractor, which require more water. This corresponds to approximately 42 million of cubic meter of water per year in the European Union. And the laundry effluent contains many pollutants such as perfume, phthalate, and surfactant and micropollutant as PFAS and PBD. So the aim of the Recyclo project is to develop a technology to treat the wastewater from laundries and to reuse it in the washing process. The treatment should eliminate at least 90% of the emerging pollutants. We are also looking for complete disinfection of the water, of course, and we want to recover the sludge form to valorize it by composting or anaerobic digestion. So the aim is to recycle between 50 and 80% of the wastewater, depending on the need of the laundry and the economic aspect. And it is not possible to recycle 100% of the water because some of it will be lost in the sludge or during the refining process. So the project is taking place in 3 European countries, so in France, in Luxembourg, and in Spain, and each with a partner laundry. So we have Groupe FRN Laundry in Spain, Clean in Luxembourg, and BSG in France. These 3 laundry will receive a recyclo pilot, and we have decided to choose 3 laundries with different sizes, from small to medium size. The University of Lyon Pop Science are part of the Recyclo project and are in charge of the communication and the dissemination. And we are also working with the Catalan Institute for Water Research. And this institute has developed method for quantifying micropollutants in laundry wastewater. So a Recyclo prototype has been installed in the Groupe FRN Laundry based in Girona in October 2023. And the monitoring will last for 12 months, and we start the monitoring in November 2023. A pilot will be set up in Luxembourg Laundry at the beginning of 2025. And finally, the last pilot will be set up in next spring in France. For these 2 laundry, the monitoring will be carried out over 6 months, and the installation will remain in place after the end of the project. So now let's talk in a little more detail about the treatment process we use. So as I said earlier, Treewater is specialized in advanced oxidation processes, and the main building of the Recyclo process is UV-H2O2, which is an advanced oxidation process. So this technology combines ultraviolet rays and hydrogen peroxide. So UV radiation activates the hydrogen peroxide to form hydroxyl radical, it's HO dot. So this radical can oxidize the organic matter, and oxidation can go as far as mineralization. So it is the formation of CO2, H2O, N2. And UV radiation also disinfects the water. So to allow the UV radiation to pass through the water and to activate the hydrogen peroxide, the water must be clear enough. This is why a pretreatment is added before the advanced oxidation module. So we have decided to use a coagulation flocculation treatment that eliminates suspended solid and also particular and colloidal COD. So the UV transmittance increase and therefore improves the efficiency of the advanced oxidation process. And finally, a finishing treatment is required to eliminate the refractory organic and inorganic pollutants. We have decided to test 2 finishing treatments: adsorption on activated carbon, it's the one we have chosen for Groupe FRN Laundry, and reverse osmosis for the 2 other pilots. The activated carbon will remove organic matter, so ions will remain in solution, and reverse osmosis can remove everything. So we analyze the wastewater of the Groupe FRN laundry. So the effluent from the laundry is basic with a pH of around 8.5. It has a COD of 1 gram per liter. It contains mainly anionic and non-ionic surfactants. And we can find micropollutants in varying quantities. So we found DHP, hydrocarbon, and PFBR, which is a PFAS. And the quantity of micropollutant will depend on the garment clean. So the laundry at the Groupe FRN is a small one, producing only 4 cubic meters per day of effluent. So the pilot plant was designed to treat 50% of the wastewater, so 2 cubic meters per day. This 50% is due to the fact that during the washing process, only the cold water will be replaced by the treated wastewater, because hot water have a different circuits. But for the 2 other pilots in France and in Luxembourg, we will reuse 80% of the wastewater. As you can see on the picture, the pilot is compact, quite small, with a ground surface area of 10 square meter, including the storage tanks. So here you can see on the foreground the electrical cabinet, which control the station. And the station is connected to internet, so it is possible to control it remotely. Here it is the coagulation flocculation module with the 3 cans correspond to the coagulant, the flocculant, and the base. Here you can't see it, but there is filters to separate the sludge from the clear water. On the middle here, it is a UV H2O2 reactor. It is a stainless steel cylinder with 12 lamps. And on the left, here it is the activated carbon tank. For this pilot, we put 400 kilograms for 1 year, approximately. And there is also 2 storage tanks for the wastewater and for the treated water in black, but you can't see them very well on the picture. So after the 3 stages of treatment, the COD is less than 50 milligrams per liter. More than 90% of surfactants have been eliminated, as you can see. And the water is well disinfected. There are very few metals in the laundry effluent, but the treatment does remove metals such as aluminum, iron, and zinc. These first few months, so the pilot is in Groupe FRN since November, so 6 months, have enabled us to optimize the process and to solve various technical problems. So these results need to be confirmed and consolidated over the coming months. So the Catalan Institute for Water Research has monitored the presence of micropollutants such as endocrine disruptor. A total of 116 molecules were studied. Analyses are still underway as quantifying them in this complex media is complicated, and the laundry wastewater is a complicated media, complex media. These early results show that DHP, which is a phthalate used as a plasticizer and a fragrance carrier in a laundry detergent, is eliminated during the first 2 steps. And it is the same for diclofenac, which is an anti-inflammatory drug, and 1H-benzotriazole. It is used as a UV inhibitor, for example, and they are completely eliminated during the first 2 steps. So the recycle process provides effective treatment of the wastewater. The micropollutants are removed, the water is disinfected and safe to be used. The sludge has been characterized and it can be valorized by composting. And we have carried out washing efficiency tests, and the treated wastewater enables the clothes to be washed properly. The follow-up will continue until the end of October for the Groupe FRN prototype, and more analyses are underway on the micropollutant present and on their removal by the recycle process. And we are currently working on microplastics. Detecting and characterizing microplastic in laundry wastewater is complicated, and we have recently started a collaboration with the French Institute. And we are also focusing on the presence of PFAS in the wastewater. So for now, we have detected the presence of only one PFAS, the PFBA, out of the 20 PFAS in the decree. And next year, so we will implement the 2 other pilots in Luxembourg and in France. So I would like to thank the people in the Life Recyclo project, so the 3 Laundry, Pop Science, and ICRA. If you are interested in our project, you can follow us in LinkedIn, on our website, or on Twitter. And thank you for your attention. Sorry, thank you for your attention. And if you have any question, I will be very happy to answer.
Thank you very much, Lisa, for your interesting presentation and an interesting the last part of the presentation about the possibilities to upgrade and the new pilots to be tested that will be focused not only on water treatment, but also the removal of some pollutants, microplastics, PFAS, and so on, that are now concerning to the industry, not only the problem of water scarcity, but also the problem of chemicals present in water. In fact, this issue is very well linked to the second session of the webinar that would be focused on the removal of pollutants from water. Our first speaker of this second part of the Life Anhidra webinar will be Carla Silva from CITEF. He's already in the screen. Hello, Carla, and thank you for attending and participating in the seminar. We'll provide a presentation about the LIFE Cascade project, which is focused on the multimodal removal of different pollutants from water. So the floor is yours, Carla.
Thank you. I'm trying to share my screen. Let me just see if I can share the presentation. Moment.
It's already in full screen. Thank you.
Okay. You can see it, right?
Yeah.
Okay, so hi, good morning. Thank you, Oscar, for the invitation. So moving to the section of today's meeting, I will present a Cascade project. But before starting, I will just give a brief overview of CITEF. So we are the Portuguese Technological Center for the Textile and Clothing Industry. We are based in the north of Portugal, very close to Porto. It is a region very, very strong in the textile industry. So we have the full value chain of industry around in a range of 50 kilometers from our center, and that's why we are based here. But we also have delegations worldwide where we have office of CITEF. Our main services is the testing and also the product and process certification by one side. We also have a huge amount of people working on high-level training and coaching and the support to innovation in the industry. And last but not least, we have the R&D team. And in particular, we are strongly doing research in sustainability, in the bioeconomy, also in the digitalization of industry, and other process optimization. And finally, we are sectorial based in terms of research and in terms of applications. So our goal when we do research projects is oriented them to the market because there are specific needs of the market. And now moving to our project, Cascade. This project started only October last year, so we are still in the first year of the project, and it will last for 4 years. And it is led by the Centro Tessile Serico Sostenibile in Italy, and also we have different research laboratories and universities that are participating in this project. Like the Politecnico di Milano, University of Insubria and Brescia, and also different organizations and wastewater treatment like Como Aqua. Why we have set up this project? The main motivation, and as you have heard in the previous presentations, there are a lot of chemicals that are emerging contaminants and that are present in water and wastewater, and they are a concern and they have to be addressed by the research, not only by the researchers, but also by the governing bodies, because they have huge impact, not only in the environment, but also public health. And one of the approaches that we have been using is the prevention strategy, so to limit the use of these substances. But in particular for some of these projects, and for instance, for the fluorinated compounds, where there's been limitation on the use of, for instance, FFCs 8, so fluorocarbons with 8 carbon molecules or more, they are completely banned. But the idea was to remove even C6 fluorocarbon chemistry, but there is without great success, because the problem that we are facing is that we lose the functionality, or we are not having real alternatives to have the repellency. That's why we need to have not only prevention strategies, but also control strategies. And to have control strategies, we need, by one side, to develop methods to quantify these micropollutants, and by the other, to develop specific technologies to remove these micropollutants from water, and in particular from wastewater treatment plants, which is the focus of our project. So we are in Cascade, we are focusing on 2 emerging micropollutants, the perfluorinated compounds, PFAs, and also microplastics. So PFAs is one of the most concerning micropollutant. It has been proved that it has not only a strong effect on the environment, but also on human health. And by one side, it's quite nocive to the environment and human health, but by the other, we don't have really alternatives to the replacement of these micropollutants from products. And it is being very used on the treatment of textiles and carpets and upholstery textiles for the repellency effect. And when we have alternatives for water repellency, when it concerns to oil or grease repellency, we don't have alternatives. And that is the reason why it's still being used in this industry, this compound. The other is microplastics. Microplastics have been detected in several sources, not only on waters, but also organisms, and they are a concern. And for microplastics, we consider every solid particle that has dimensions from 1 to 1,000 micrometers, but we can go even larger dimensions, to 5 millimeters. And these microplastics are the result of the use of a degradation in the environment of products that are formed by synthetic polymers like polycarbonate or polyester. And in particular for the textile industry, they are the result not only of industrial operations, so during the washing and treatment of textiles, but also from consumers at their home when they do their washing of their clothing. So the aim of Cascade project is to detect these 2 micropollutants, and to implement different technologies that are able to remove PFAS and microplastics from wastewater. And these technologies will be implemented not only on the textile companies, but also on centralized wastewater treatment plants. And in particular, CITEV is being in the project to have a role in the quantification and qualitative and quantitative assessment of the microplastics that are in the wastewaters. So the project that is in the first year of starting has 3 main levels of implementation. The first level will be dedicated to the analysis. The second level, and one of the most important, will be dedicated to the removal of these micropollutants and demonstration. And the third level is to measure the impact on the waters after the removal of these micropollutants. So for the first level, we have already performed a series of surveys into textile industries, not only in Portugal, but also in Italian companies. And the idea of these services is to characterize their processes, what raw materials they are using, what are the chemicals that they are using, what are the emissions that are foreseen in terms of microplastics, but also in terms of fluorinated compounds. And then the target is to assess and quantify to support the next stage of the removal of these micropollutants. So for the detection and quantification, and in particular for the microplastics, it is true that there are several technologies available, there are several standards, but the problem is, and the previous talks you also heard some of this point, the problem is when you have complex wastewater. So it is simple or is simpler when you have clean controlled waters, when you control what is the textile that is there, when you have simple matrices. But when you go to complex matrices like those that you found in wastewater treatment plants, or even the discharges from the chemical, the textile industries, we have a series of challenges, and there's a series of false positives that we are detecting, and that is really making complex to detect with a real certain the presence of microplastics. So we are exploring different methodologies by pyrolysis, also micro FTR at CITEV, where we are optimizing the methodology to be able to have by visual images the specific identification of a microplastic and the type of microplastic. So if it is the origin is polyester or polyamide or elastane, we will be able to analyze it and quantify in our treatment waters. And also using Nile Red as a dye that is able to color these microplastics, but it has also limitation that it links to other organic matters. So the second stage that we'll start is to develop methodologies to remove these micropollutants from the wastewaters. And these methodologies, this treatment will be installed, as I already mentioned, not only on textile industries, but also on wastewater treatment plants. And the idea is to quantify the inlet and the outlet, and to have the impact of the removal and the efficiency of these micropollutants. And in particular, we are getting a focus on the microfiltration and nanofiltration separation, and also absorption on activated carbon for this removal. And finally, the third stage will be dedicated to measure the ecological impact and of the mitigation measures on the removal of these micropollutants, and what is the impact on the environmental ecosystem. So we will have monitoring campaigns where we will be evaluating the levels of PFAS and microplastics in the waters, and this will be performed in the Como region. Then we will have the evaluation of the ecotoxicity in different effluents using different organisms. And finally, we will perform a series of mesocosm studies to evaluate the ecotoxicity of treated wastewater treatment effluents and the response in the environment to the presence of PFAS and microplastics. And as the expected results, the first and probably the most important at this stage will be the development of analytic methodologies for characterizing the PFAS and microplastics. We also are having a strong effort on developing treatment technologies. As I mentioned, these treatment technologies are aimed to the textile dyeing and finishing companies, but also to the centralized wastewater treatment plants. Then we will evaluate ecological impacts of these waters after this removal, and install these technologies for demonstration that will be in Como Textile District, but also the Portuguese Textile District. And this is all. Thank you for your attention, and I'm open to any questions you might have.
Thank you very much, Carla, for your presentation. That is also focusing and paying attention to this kind of emerging pollutants. Some of them widely used by the industry, not only the textile industry, like the fluorocarbon-based compounds that promotes water and oil repellency on textiles, but also promotes anti-friction properties or anti-soiling properties in other type of materials like glass, like metal, for example, and in fact, this kind of treatments on metals and this kind of pollutants on metals are in which the next presentation is focused. That will be released by Luca Magagnin, that I think is also attending here.
Yes,
I'm here.
Hello. Good morning.
Hello, good morning. Luca comes from the Politecnico di Milano and is going to provide, to release a presentation about the removal of PFAS, PFOAs, exactly in the metal industry. So, Luca, please.
Thank you very much for your introduction and for the organization of the
Welcome.
day. Yes, I will show you some results about, let's say, the removal of PFOA with the magnetic fluids. This activity is part of a larger project, which is a LIFE project called Fontaine, which is dedicated to the monitoring and removal of PFAS as a general, specifically from, let's say, surface waters or wastewater related to the surface finishing industry. I will give you some other details later. Here, the main goals of the project. You see, there is we have completed more or less the first year of the project. As you see here, we have basically three main phases or goals. The first one is the monitoring, and the idea here is to try to develop a technology that can be integrated on industrial lines, typically used in the finishing industry, or even where they collect the water from the wells. To be using the line. And so the idea here is to develop a technology able to monitoring PFAS. Let's say we know that we have many PFAS, and so we are now focusing on some of them in situ, so directly let's say in the line. I will show you just a slide later here from this part. Let's say the main technology that we are using here or implementing here is Raman spectroscopy. The second goal is to capture these the PFAS, and so we want to completely remove these PFAS from waters, and so we use functionalized magnetic particles that we can call also magnetic fluids. There is it's not implemented yet, but there will be also a part dedicated to the degradation of the PFAS supported on the particles through electrochemical advanced oxidation. The third phase, which will start say with the next year, is the demonstration activity, which includes let's say the installation of a pilot plant for the treatment of waters, wastewater or surface water, in order to completely remove PFAS. Regarding the first goal, as you see here, the idea is to the in situ on-site monitoring, and so the idea is to use a Raman spectroscopy in the version defined as SERS, so surface enhanced, and so we are basically implementing the substrates and so to achieve the enhancement of the Raman signals, and so to detect directly in the line the presence of PFAS. Going to the main part, let's say, of the results I'm going to show you today. The technology is based on the use of magnetic particles. So we have, say, a long experience as a research institute, but also with some partners of the project in the use of magnetic particles for the removal of contaminants, which can be metallic ions, organic contaminants, and now we are applying these also for PFAS. Of course, the idea here is that magnetic particles can have a couple of advantages. The first one is very easy to prepare, even at the, let's say, as a larger, let me say, so micro scale particles, but constituted by aggregates. So the surface area of these particles can be very high. And so also the absorption capability. And then they are magnetic. So you can choose, you can decide to use them as dispersed in the water and that collected them with a magnetic filter, for instance, or in traditional way as supported on like paper in the filters, as it is usually done with other systems like carbon, for instance. The advantage is that magnetic particles can be also completely recycled. So once you decide that they are not efficient anymore, basically you can dissolve them and reuse and regenerate completely the particles. The approach to remove PFAS as a general, and here applied to PFOA. You see here we have a couple of, or at least today I will show you a couple of approaches. The first one is, you see here the particles. Here is defined nanoparticles, but actually it's micro because they are aggregates, as I said, of nanoparticles. We have developed the proper functionalization in order to interact with the fluorinated molecules, and then we try also to implement a new kind of system, again supported on magnetic nanoparticles, but you see now typically without any presence of fluorine or fluorinated molecules. For this first step that I'm going to show you, that I'm showing you today, you see here, so we have the preparation of the particles, then the mixing, and so in this case as a batch system. And then of course we, apart the characterization of the powder, we have all the procedural protocols for the measurement, in this case, of the residual content of the molecules in the water, typically using HPLC. Here some results. Let's say apart the ratio between particles and the amount of fluorinated materials, this is again, these are preliminary. I'll show you some preliminary results, but it's something that we are trying to optimize. But you see that it is very dependent, the efficiency that you can achieve on the functionalization that we are able to apply to the particles. Let's say, just to be clear here, we use functionalized particles with different kinds of functional groups. We put the particles in contact with water, and then we extract using a magnetic filter or magnets. But in any case, if you adjust properly the functionalization, you can see that you can go up to 95%. So we think is a good, let's say, percentage of removal, considering that you completely remove the molecules from water without releasing any byproduct. Let's say, a point that we are still evaluating is the contact time or the extraction time, because usually this kind of technology based on functionalized particles should be very fast. Actually, you see here that with the PFAS, it needs some time, so at least 20 minutes to achieve a very good efficiencies. And so this is also part of the activities now today in order to see how to implement to reduce this treatment time, maybe with a multi-step process. Here we see an example of the other system, so with the metal organic frames, again supported on magnetic particles. We see here the efficiency can be also very high in terms of extraction. The other interesting point is that you can use this system, let's say, regenerating the particles many times. And we have tested up to 10 extraction when we saw the first important decrease in efficiency. Of course, all technologies have advantages and disadvantages. So the first example, using functionalized particles with fluorinated molecules can be very selective. For instance, we have confirmed the regenerability, very easy to synthesize, but again, we have a fluorine species around. So it depends on the legislation and all the other aspect. Is a possibility. We have to see what how this technology will be accepted in the future. Regarding the metal organic frame, again, very cheap, of course, because we have to transfer this technology at the industrial level. The efficiencies are very high. Let's say, part the regenerability that we still want to confirm, probably the selectivity is less effective with respect to the first solution. We have to see if this actually is an advantage or disadvantage, because it depends on which other species we are able to collect. I just use again this last this slide that I've already shown, just to focus on the phase 3, because as you see here, the LIFE project, the partners of the LIFE project are reported here, are basically located in the north of Italy. Gaser, which is one of the main surface finishing company in Italy, is located in the Veneto region, together with also PD Service. Captive System is the startup which is providing the technology of magnetic particles, and then Asfimet for the dissemination and exploitation of the technology. But as you see here, basically the two companies involved actually now, following an invent with 3 companies, again located between Lombardy and Veneto, and you may know that this region is for sure affected by the presence of PFAS in the surface water, so it's a huge problem. And so the next year, for sure there will be a pilot plan with the idea to treat, say, hopefully up to 30-35 cubic meters per day of water in the Gaser premises, so to treat the water that we collect from the wells and use this water directly in the finishing line, so to reuse the treated water. So thank you for your attention.
Thank you very much, Luca, for your interesting presentation that is focused, as we talk about, in a high concerning problem about this kind of micropollutants, emerging pollutants, and so on, and how the micro and nanomaterials can provide some interesting solutions to the industry, and not only the metal industry, but maybe other industries that are using, for example, PFAS in their manufacturing products. And in fact, nanomaterials can provide interesting solutions. So Massimo from Project Hub is also going to provide another point of view about the use of nanomaterials for water treatment, and how sustainable and safety issues should be considered for the application of this kind of nanomaterials in this kind of treatment. So Massimo, please, the floor is yours.
Thank you. Can you hear me?
Yeah.
Okay, I try now to share my presentation. Can you see it?
You're currently sharing your screen, yeah?
Yes, I'm trying to go in presentation mode. Can you see it now?
Yeah, it's full screen.
Okay.
Thank you.
Okay, I don't see you anymore, but please, if anything, you can help me.
Yeah, Massimo, I don't know if the volume of your laptop can be increased just a bit.
This is
or your microphone.
Oh, the microphone. Can you
Yeah,
hear me better now?
Yeah, it's okay.
Okay, because it's quite directional mic, so okay.
Okay.
I try to get closer. Okay, so today I will talk about the Integrano project, which is already started, and today we will have the 6-month meeting assembly, so it's a little bit overlapping, but I made it to be with you today. So thank you for all participants and for the interesting presentations. This project was written by Project Hub and gathering many other partners with a specific expertise, and it has many nanomaterials portfolio in its say main tasks. But it is also focusing on some specific application on water treatment. So one of the many nanomaterials and applications addressed will be somehow inherent to this today workshop. So just a few words about the project. This involves 13 partners, 8 countries. It is a 4 years project, and it has about 4 million funding. This is belonging to the Resilience Call 2023, and it's a research project basically. So it will be finished in 31st December 2027. This is the group of partners involved, and you see that there's a very good European coverage and also many specific and complementary contributions from material science, toxicology, characterization, industrial application, etc., etc. So the project was somehow deriving by the experience of many other projects and activities carried out in the last, say, 10 years related to the nanomaterials, to environmental impact assessment, to toxicology and nanotoxicology, in order to somehow put a common denominator to the safe and sustainable by design, which is a quite hot topic now, very discussed, and a lot of European effort is provided to address this challenge, which involves the safety of materials, chemicals, and nanomaterials, their environmental impact, the economic impact, and the social impact. So by gathering different expertise, it was possible to leverage this experience and expertise within Integrano project. The projects that we are referring to as a source of good experience in nanomaterials applications are product project, the Xena project, which was the one mainly devoted to the study and development of safe and sustainable by design methodologies, and other technical oriented projects on specific material, bio-based materials for different industrial applications such building construction, textile, biomedical, and as well as fish and fish industry and fishing gears production to be more sustainable within the environment. So I would like to share with you the main concept of Integrano, which is following the safe and sustainable by design framework and guidelines provided by JRC. One of the novelty of Integrano is that it's a quantitative based assessment to say safe and sustainable by design. So it implies metrics and measurement and elaboration of data. So it's not based on qualitative approach. It's important to say that it's case specific, and it provides a relative comparison within the same set of samples or technologies or alternatives that are being addressed in the case studies. And it also considers the concept of more sustainable and safer based on base available technologies, not pointed to absolute sustainability, absolute say safety, which doesn't exist, but to be as better as we can based on the time, cultural, technological constraints that we are involved in. Then it's important to say that the approach is case specific. So we are developing specific experimental design and experimental campaigns for characterization, synthesis, toxicity assessment of nanomaterials, their incorporation, addressing use phase, etc. So we also exploit existing frameworks, so we are not inventing from scratch anything new, but we want to leverage what is already existing and to obtain a more specific implementation to safe and sustainable by design. Then the main concept is by correlating options, alternatives, which we call key decision factors, and to correlate with them with the key performance indicators in the different dimensions like environmental, social, safety, human safety, ecotoxicity, etc. And in order to obtain solutions, we applied a multi-criteria decision analysis algorithm that have already been implemented, partly implemented within the Asina project and now leveraged within the Integrano project for specific applications. As I was mentioning, we have different dimensions like environment, cost, so economic sustainability, safety for humans and for the environment, so ecotoxicity and toxicity, human toxicity is assessed, and then technical performance, which is not disregarded because we cannot, of course, address sustainable solutions if they are not technically performant. So there would be no business case, no industrial application. So all these KPIs and KDF will be fed into the decision support system, which is implemented in multi-criteria decision analysis algorithm to obtain safe and sustainable by design solutions. As I was mentioning, we have different life cycle phases from raw material extraction to the synthesis phase, the incorporation of nanomaterials in coatings or in bulk composites, the use phase analysis, and the end of life. So this is a full life cycle from cradle to gate or from cradle to cradle in the circular model framework. And this will allow defining life cycle stages analysis and then to get quantitative data by data generation in the different dimensions like in environmental, costing, social, performance, and safety. And then we have data curation and harmonization of obtained data for final analysis in the SSBD framework and computational tool. So the goal of the project is to support decision-making, but with a human-centric approach to promote the advanced material innovation, generation, and application. And we also allow reducing the R&D approval lead time. We minimize the costs and increasing data transparency when providing results. So this is very important for industrial application in terms of time to market from concept to implementation. And then we sustain a new strategic research and innovation plan for chemicals and materials to implement a safe and sustainable by design framework, and then support the industry by reducing research and technological development and innovation risks. So I want to, since time is flying, I want to skip some slides and get maybe directly to the application. So we, as you see here, we work on different industrial applications, cosmetic, air filters, water filtration, water membranes, and this will be a topic that we'll discuss today briefly because it's an ongoing activity. Basically, for this case study of water treatment, it's a post-industrial water treatment, we consider the synthesis of nanoparticles, their incorporation phase, and the use operation testing phase. The case study is focused on the synthesis of cerium-doped strontium ferrite silica nanopowders, which exhibit thermocatalytic properties, and biosilica and titania nanoparticles, cold shell nanoparticles with a bio-based source that are, say, the active that will enable the water purification step in the TPPR, thermocatalytic packback reactor system, which will be created through the post-industrial waste from membrane generation, from silicon carbide debris, which will be coated with the active nanoparticles. So as you see here, the sketch is the testing unit that is being implemented in order to test the ability of destroy contaminant of emerging concern and very persistent molecules that are polluting water. Some of them we were hearing this morning in the very interesting presentation. So what I would like to highlight in this case study is that we are really addressing the whole life cycle, and we of course address the functionality, so the abatement performance of this system and of these nanomaterials, and we compute their environmental impact through all the life cycles, from the generation of nanomaterial through the use and operation of the units. And we consider also the social impact of the addressed options that we are considering, the costing analysis, and of course, last but not least, the safety issues related to the synthesis, incorporation, handling, human exposure, and operation, also by testing leaching of potential leaching of nanoparticles into the purified water. So this is a holistic perspective in order to prove the safe and sustainable solutions in water treatment. Just a few words related to the KDFs, to the key decision factors, and to the KPIs. So we are considering different synthesis parameters as a key decision factors that will impact on those dimensions that I was mentioning. And we are also investigating different incorporation technologies and incorporation parameters once the technology is specified. So you see that the matrix of experiments and of quantities to be assessed is quite huge. And for this purpose, we adopted these algorithms in order to deal with this massive amount of data, which are case specific and allows us to get the real multi-optimal solutions that we are addressing to. Just to inform you that Integrano is also promoting the exchange of best practices of knowledge among different projects, among different innovation experiences, application experiences of chemicals and nanomaterials, as well as the sustainability assessment methods and frameworks. So coming in September 2024, we will launch a knowledge and data exchange hub that will perform all these activities, including workshop seminars. And so all people are kindly invited to contribute and do participate according to the interest and expertise. I would like to thank all the partners that are involved in the project, which are already very active. We are at the 6 months meeting, but very fast and productive. This is I'm honored to somehow co-coordinate this activity with our team in Project Hub and supporting Milano Bicocca as coordinator in this interesting challenge. So these are the references for the project, and thank you so much for the interest in this topic. So as soon as new solutions will come up, we will of course keep informed, and you can follow us through the Integrano website and all the socials. Thank you so much. I hope I was on time.
Yeah, thank you, Massimo.
I'm now
thank you very much. Thank you for your presentation and also the effort of Intergrano for attending and participating in the webinar, because we know this week is very busy for you, attending several events, including your consortium meeting. Okay. So thank you very much.
Thank you. I'm not able to now get the control of the thing. Yes, maybe. I want to interrupt the sharing. If you can do for me to just drop me out of the sharing mode so that you will be able to proceed. I don't know. I don't have. Oh, now okay, clear.
Now I have the.
Great.
Yeah.
Thank you, because I was unable to find out the control panel. Okay.
It's okay.
I'm
it's
following.
Okay.
Thank you so much.
You're welcome. So we have already completed the two first sessions of the webinar. You can see also the agenda here. So we are going to go forward with the third session that will be also focused on water treatment, but not only water treatment, but also what can we obtain for this water treatment, and we can consider water not only as a resource but also as a raw material, but and a source of different maybe products, interesting products, raw materials, and subproducts that can be used for different end applications. So I'm going to give the floor to the next speaker, that is Marta Elvira Castaño, that is coming from Aqualia, and is going to present the main goal and main results of the LIFE Zero Wastewater project. So Marta, please.
Good morning, everybody.
Good morning. Hello.
I'm going to share my screen. Okay.
Okay, it's in full screen. Thank you.
Okay. So, first of all, I would like to express my gratitude to being invited to participate in this event and share this time with all of you. Today, I will talk to you about Life Zero Wastewater, which combines anaerobic and autotrophic bioprocesses to transform a wastewater treatment plant into a resource generation biofactory with a positive energy balance. Okay. To begin with, I would like to focus on different scenarios that I think you are likely familiar with, and which give meaning to this project. So first, nowadays, as you know, wastewater treatment plants continue using activated sludge process. This process wastes a lot of energy. 60% of the total energy consumption in its wastewater treatment plant is from aeration processes for nitrogen removal, and it is a high waste of energy. So it's important to find new technologies which replace this process. On the other hand, there are some problems with some resources, such as phosphorus, which is important for fertigation and is a non-renewable energy, renewable resource. And we have to search for new ways to obtain this resource. Also, water scarcity, as you said before, it's a problem in a lot of countries now, and the need to replace non-renewable energy sources. Finally, the solid bio-waste, each person generates a lot of solid bio-waste per year, and it needs to be transported and to be treated, and it generates a lot of emissions. So it's another problem, and these problems give the sense of our project, no? Okay, so Life Zero Wastewater is a project developed by 6 different companies and from 3 different countries. This project is about the combined treatment of urban wastewater and the organic fraction of municipal solid waste in wastewater treatment plants with a positive energy balance for small locations. This project is carried out in a demo plant, which was located in Madrid, Spain, but now is located in Almería, also in Spain. And the line of the project you can see in this diagram. First, the collection of the organic fraction. We want to obtain this organic fraction from different origins, such as kitchen waste or restaurants, hotels, or the solid fraction, organic fraction of the solid waste. Then this organic matter is implemented in the wastewater, and enter in a treatment plant. This treatment plant consists in 3 units. The first one is the anaerobic membrane bioreactor unit. The second one, partial nitrification Anamox unit. And the final unit is for the nutrients recovery. Then I will explain more in detail these different units, and they could be combined in a different ways depending on the final product, if you need nutrients, if you don't need it, and your necessities. Okay, the project objectives are first, the collection of 125 kilograms per day of organic fraction. Now we are collecting it for a restaurant, catering, and greenhouses in our demo plant. Also, the treatment capacity of 50 cubic meters per day, including wastewater and the organic fraction. The production of biomethane in the anaerobic reactor. The reduction of in biosolids compared to the baseline, the conventional treatments. The recovery of pathogen-free water for reusing, and the recovery of phosphorus. Obtaining 0.2 kilograms of soil fertilizer per cubic meter, and more in general, a positive energy balance and good control of the process with online monitoring software. Okay, so now I'm going to show you each unit of the demo plant and its benefits. First, the demo plant has an organic fraction unit where we have a table with 2 sinks, and in each sink there is a grinder. This grinder grinds the organic fraction, simulating a real-life situation in a kitchen of any house. The implementation of the organic fraction in the wastewater treatment have some benefits, such as the increase of the organic content, the increase of the biomethane production, not to generate emissions in the transport of the waste, of the organic waste, and it helps also in the growth of the bacteria inside of the anaerobic reactor. Okay, the mixture and with wastewater and organic fraction enter in an aerobic reactor from a ANMBR unit. This reactor is a 100 cubic meters reactor in our demo plant, and it has a gasometer for the biogas. And then we have 3 ultrafiltration membranes from different suppliers. These membranes have similar characteristics, but are from different suppliers because we want to test their work. This process, anaerobic process with filtration procedure for treating wastewater at room temperature, is a process developed by the University of Valencia and Aqualia, and we have tested in another projects before. We in this unit we obtained biogas and we obtained the permeate of the membranes, which is a water with high qualities. To test these qualities in terms of pathogens, we use the coliminder, which is a pathogens equipment with measure online the concentration of pathogens. Here are some results from the operation time. We continue operating the demo plant, but at the moment we have little results, and for example, the removal of the COD, of the removal of the total solids of the inlet water. Okay, the next unit of the demo plant is the partial nitrification and ammox unit. It consists in 2 reactors. The first one is the partial nitrification reactor, where the 50% of ammonium is converted into nitrate by ideation. And the second reactor is the anammox reactor, where anammox bacteria combine ammonium with nitrate to obtain nitrogen gas. This process was also developed by Aqualia, but with the University of Santiago de Compostela, and its name is Aquelan. Okay, here are some results of the process. You can see how the ammonium concentration decrease while the nitrate concentration increase. And the benefits of this unit is that we don't need a lot of energy, because there is a 60% reduction in oxygen demand, because the partial nitrification needs a little oxygen demand. The anammox unit works without ideation. Also a total reduction in required organic matter in comparison with the conventional treatment, and a 90% reduction in produced biomass. All these data in comparison with conventional treatment that we use nowadays. And finally, in our demo plant, we have a nutrients recovery unit. This unit consists in 3 adsorption columns with different materials. These materials have been tested in a jar test and show good results, but we have to continue working with them. Some of them are wollastonita, Fosflow, Ferrolox, Thermax resin, and Purolite, and they are very different, but it show good results. So with all of this data, we obtained a positive energy balance, having in account the energy consumed and the energy produced with the biomethane produced in the anaerobic reactor. And economic balance also positive, as you can see in these graphs. So that's all. Thank you for your attention and hope you like it. Thank you, Marta.
Thank you very much for this presentation and to provide a wide overview about what are the modern wastewater treatment plant, not only a place for treating water, just treating water, but also a kind of biofactory in order to generate some resources for different industries. So we are going to move forward for another example of this kind of smart water system and smart water plants for treating water and to recover some resources from wastewater. Next speaker is Joep van den Broek from KWR from the Netherlands. Thank you, Joep. Welcome.
Thank you. Good morning.
And good morning, and he's going to provide a presentation about symbiosis, industrial symbiosis, and the ultimate EU project. So please.
Thank you, and thank you for the invitation to present something on the ultimate project in this very interesting webinar. So what I'll do in the coming 10 to 15 minutes is quickly go through the project Ultimate, which deals, as Oscar already mentioned, with industrial symbiosis, and in particular with what we coined as a term, water smart industrial symbiosis. So a few words about the project itself. So Ultimate is a project under the Horizon 2020 program, actually one of the last projects to start in this program. The project started in May 2020, and we are almost at the end of the project. We will finish in October, so we are now preparing our deliverables. And for those of you interested, more information is on the website as shown here. The project has a consortium of 27 partners from all over Europe. I'll show you the countries involved later on in the presentation. And I have to say, we deal with industrial symbiosis, but textile industry is not one of the industries represented in the project, but we deal with a number of other industries. And I think the results are relevant also for the textile sector. So what is the project about? Ultimate stands for Industry Water Utility Symbiosis for a smarter water society. And what we do in the project is we look at developing, optimizing, and demonstrating technologies and solutions for water reclamation and water reuse. Also, the exploitation of energy and heat that is present or contained in, for example, wastewater. And we look at nutrient and material recovery and reuse also from wastewater. In total, 9 case studies looking at different aspects using different technologies to look at these 3 elements. And then all the innovations that are developed in Ultimate, that's an interesting site to go to. All of the results are not only found on the Ultimate website, but also in the so-called Water Europe marketplace, which is a digital environment with the results from a number of European projects, including Ultimate, but also Be Water Smart and NextGen, which also deal with circularity. Now, for those of you not familiar with the term industrial symbiosis, so what do we mean when we talk about industrial symbiosis? Well, industrial symbiosis is basically the cooperation between companies that provide them with mutual benefits, economic or environmental. And in the context of circular economy, it deals with the exchange of materials. So the use of the waste stream of one industry as the resource, the input of another industry, for example. So it's about turning waste into resources, circularity. And then in the ultimate project, we deal with the water aspect of industrial symbiosis. So we focus on the water streams, and that's why we call it the water smart industrial symbiosis. And one of the, let's say, iconic industrial symbiosis in the world is the site in Kalundborg. Kalundborg is in Denmark, a larger industrial site which has been operating with this industrial symbiosis principle already since the 1970s. And Kalundborg is also one of the case studies in the ultimate project. So what do we do in the project? Well, I already mentioned technology. So in ultimate, we look at demonstrating on pilot or even full-scale technologies for the recovery and reuse of water, materials, and heat. But we also look at the supporting ecosystem. So we look at how can we make sure that we not only demonstrate that the technologies function, but that we can also speed up the implementation and the replication of these technologies in real day-to-day practice. So to do that, we also look at digital tools to support design and decision making. We look at creating the ecosystem in which these systems can thrive. So we look at communities of practice, living labs where things can be tested. We look at also at business models, so water and energy and material recovery. How can we make that a sustainable business practice as well? Building the market for these type of solutions, and then through the actions in the project, also strengthening the collaboration between the relevant partners in the scene. So if we then dive into the heart of the project, which are the case studies, I already mentioned we have 9 case studies spread across Europe, represented on the map here. And in these case studies, we combine collaborations of industries with service providers. Industries, for example, are the agri-food sector, beverage industry, chemical industry, and also biotech industry. And in each pilot site, in each case study, one of these industries works with a service provider, which might be a municipality or a private service provider, which takes care of water treatment, providing, for example, industrial water from reclaimed municipal wastewater. And the industry provider could also be the organization that utilizes, valorizes the energy or the materials recovered from the waste stream. So it's that type of collaboration that is fundamental for a successful industrial symbiosis, and which we also stimulate in the project. Well, I already mentioned that next to the demonstration of technologies itself, we also look at how to exploit, how to valorize the materials recovered, or how to valorize, exploit the technologies developed. So that's why in Ultimate we have a separate work package actually looking at value change for the recovered materials, but also for technologies where we look at arrangements between industry and the water service providers. So how can they actually collaborate? Looking at partnerships, for example, but also co-ownership is an option, or developing new services. So this is part of what we do in the project as well. And this is all supported by analyses of, for example, the recovered resource streams, doing risk assessments, both on microbiology and chemical risks, but also looking at life cycle assessments in terms of costs and also environmental footprint. So this is all included in the project. Then another pillar in the project is stakeholder engagement. So there's a number of activities in Ultimate that focus on the inclusion of stakeholders in the development, in the demonstrations that we do. And that includes industrial, so business stakeholders through communities of practice, exchanging the results, but also the needs from the different organizations in the industrial sector. It's also focusing on outreach to the public, because our idea is that a successful implementation of the industrial symbiosis concept also needs support, it needs understanding in the broader society. So we look at including stakeholders in these, so citizens in these case studies, and we do that, for example, through the development of so-called immersive media experiences. So a digital environment that can teach citizens. In some cases, we target young children. We target children in the high school age to teach them about industrial symbiosis and increase the understanding. And then there are living labs, which really focus on involving stakeholders in the demonstration of the technology and the functioning of the technology itself. Now, a few details, because this was all quite general about the project, is focusing on what we are doing and aiming for. What I'd like to do in the next few slides is show you a few of the case studies that we are working on, and the technologies that are demonstrated in those case studies. In total, we have 9 case studies, but in those 9 case studies, we have a total of 22 different pilot plans. So most of the case studies actually look at multiple technologies, but all of them look at least at 2 of the 3 elements that we're looking at: water, materials, and energy. And next to that, we also have a number of control and early warning systems that are developed, and a few cases do concept studies instead of pilot plans for technologies that are less mature. So a quick look at the first case study that we have, which is located in Tarragona in Spain. This is a case study where we look at the reclamation of water, primarily for cooling purposes, from both a municipal wastewater treatment plant as well as an industrial wastewater treatment plant. These 2 plants are already in operation, but we have looked at how can we improve the amount of water that can be recovered from those waste streams. And we have done that by looking at a combination of ultrafiltration and reverse osmosis to produce fit for purpose water. And then we've also looked at membrane distillation as one of the ways to treat the concentrate stream that is produced when you use ultrafiltration and RO. And at the same time, we have looked at the removal of ammonia from the municipal wastewater treatment, the municipal wastewater, to make it easier to treat. And that was done using zeolites for absorption. The RO and the zeolite absorption were successful. The membrane distillation we found is too expensive to operate to actually treat the RO stream. So at the moment, that concentrate stream is still an issue, because after RO it contains a number of contaminants that are too high to allow discharge. So that's something that needs to be investigated further before full-scale implementation is possible. A second example is the case study in the Netherlands, a location called Nieuw Prinsenland, which is a horticulture or a greenhouse industry location with a large number of greenhouses. And we have looked at 2 different components for the greenhouses. One is the storage of heat, and the other is the production of fit for purpose water for irrigation. So the heat storage is relevant in the Netherlands in particular, because the greenhouses are actually heated in wintertime using natural gas. And we have looked at making that more efficient by, for example, storing the excess heat of an industrial site in the vicinity of the greenhouses, and being able then to recover that stored heat during the wintertime to reduce the amount of gas that is necessary for the heating. And the production of the fit for purpose water we have looked at by using a technology called electrodialysis, which is a membrane-based technology that uses electrical current to remove ions from the wastewater stream, to treat the wastewater from the greenhouses themselves to make it suitable for reuse, because the main obstacle to reuse is the presence of sodium in the wastewater. And with the electrodialysis system, we have been able to remove enough sodium to make the reuse possible. Now, a few images to illustrate the storage of heat in the project. So what we have done is we have analyzed whether it's possible to store thermal energy, heat, by increasing the temperature of the groundwater, and then during the winter time to actually pump up that heated groundwater and then extract the heat that is included in incorporated in the water to heat the greenhouses. We haven't done this in practice. This was one of the feasibility studies, but we have shown that in the region where these greenhouses are located, the underground, so the conditions are appropriate for this type of heat storage, and that the efficiency of the recovery of the heat is sufficient to actually support an economically viable storage solution. Now I see that I'm running out of time a little bit, so I'm going to skip quickly through the next few slides. So the next case that I would like to briefly mention is a case in Spain, in Lleida, where we have looked at biogas production using a so-called electrostimulated anaerobic reactor to produce biogas from the brewery's wastewater. And we've also looked at heat and electricity production using a solid-state fuel cell. Actually implemented at full scale this LSAR reactor, and successful so far. And then the other example that I would like to illustrate was the work in Tain in the UK, where we looked at recovering of biogas and also struvite and ammonium from whiskey distillery wastewater using the process shown here. And I assume the slides will be shared so you can look at this in more detail after the webinar. So to conclude, we have a number of observations from the work that we have done to, as we feel, communicate with the sector, but also with the policymakers. So in terms of policy, we see that to allow for broader acceptance and application of recycling, reuse of materials, it's really necessary that a risk-based approach becomes more and more embedded. It's also necessary that there are financial incentives to stimulate those circular economy solutions. Digital tools can be used to support the solutions, for example, in decision making or in monitoring, and also the support from society as a whole is required, because often these systems are inducing a bit higher cost, and understanding for the problem and the solutions is important in that case. And then final messages. Well, as explained, water smart industrial symbiosis is a particular type of industrial symbiosis where we look at water, but also energy and materials recovered in the water. For successful transition toward circularity, we depend on a systematic addressing of the technological, but also the other dependencies like digital, socioeconomic, and governance. We have shown that there are opportunities, but we need further focus on synergies and transferability and applicability for wider acceptance and understanding. But we have shown that these type of circular solutions can really contribute to not only a more circular society, but they can also contribute to a more competitive industry. And with that, I would like to end my presentation. Thank you for your attention.
Thank you very much, Joep, for your interesting presentation and to provide how different solutions can be designed by tailor-made concepts depending the quality of the water to be treated, the pollutants to be treated, and also the expected resources to be obtained and to be generated from each one of these solutions. So thank you very much again for your presentation. Now we are going to focus and to pay attention about advanced water treatment technologies, about how the anaerobic membrane bioreactors can provide some interesting solutions for water treatment and the recovering of waste sources from wastewater. This presentation is going to be released by Emma Perez from ITEX. So Emma, the floor is yours, please.
Thanks a lot, Oscar, for your introduction. I would like to share my screen.
It's working. Okay, thank you.
You're welcome. So now I'm going to talk about the Synergies project. First of all, I would like to make a short introduction to explain why this project comes from. Wastewater and municipal solid waste volume coming from domestic activities is dramatically increasing due to the increment in worldwide population and activities in urban areas. Water pollution and overproduction of waste. Creo que tienes tu cámara o... Sorry. Which lead to shortages in natural resources, require innovations in waste treatment. This innovation must be based on a new paradigm, from waste management to a resource management philosophy. Through energy and material retrieval, wastes are considered to be a resource that can and must be drawn upon, which is the concept of waste recovery. Industrial and urban symbiosis is one of the solutions in line with the previous statement. Industrial and urban symbiosis is a strategic way of working to increase the resource productivity through collaboration. The strategy is based on a long-term collaboration between different sectors and actors that increase the value of their underutilized resources and promote environmental innovation. Industrial-urban symbiosis improves the competitiveness of the industries, reduce the emissions and the use of fossil and primary resources, while strengthening the regional development and resource security. The Synergies solutions are highly relevant factors in line with industrial-urban symbiosis by transforming waste and byproducts into green value products. The Synergies project is a European project that belongs to the Twin Transition Call. This project overall aims at developing new technologies and solutions based on the industrial and urban symbiosis concept for local and regional collaborations among diverse actors like citizens, municipalities, and sectors, improving the sustainability of the use of industrial and society resources starting from wastewater and waste materials. The project is based on the creation of 4 eco-sites in 4 European countries that will implement demonstrations covering different sectors, resources, geographical dimensions, and socioeconomic aspects. The Danish eco-site is based on food companies, including a farmer and a brewery. The Austrian eco-site is based on a meat processing industry. The Spanish eco-site is based on the textile and the cosmetic industry. And the Greek eco-site is based on the olive refinery industry. Now you would be wondering, what is an eco-site? An eco-site can be considered like a small town with different actors that contribute to its maintenance and its economic development. It's a well-connected and interactive system where everyone has a specific role. Each eco-site is based on a wastewater treatment plant, municipality, enterprises, or agriculture entities, all located in the same region. In this context, they form a hub that collects wastewater, biowaste, and non-recyclable wastes, all generated by both urban and industrial environments. All ecosites consist of an anaerobic bioreactor and an adsorption column. The treated technologies have two feed tanks, one for the biowaste and the other one for the wastewater, which will be pumped into the anaerobic bioreactor that will produce biogas to be transformed into methane or hydrogen as an energy source. After the reactor, the antifouling treated membranes will separate the sludge and water. That the last one will be directed to the adsorption column to obtain clean reusable water. The pyrolysis of the non-recyclable wastes is performed in a parallel installation, and the char is activated and functionalized with lignin nanoparticles and or carbon dots, and sent to the ecosite to feed the adsorption column. To conclude, in each ecosite, a co-treatment is developed to generate clean water, energy, several upcycle site streams like biogas and high-value new products like platform molecules, fertilizer, and polyhydroxyalkanoids for its reduce in each specific region. From the global energy crisis perspective, it is necessary to implement more cost-effective and sustainable technologies to replace the current aerobic processes that requires considerable amount of energy for organic matter oxidation. In a conventional wastewater treatment plant, this energy demand accounts for more than 50% of the total energy consumption, and a large amount of poorly biodegradable biomass is produced. These drawbacks have increased the interest in anaerobic processes, since they have the potential to be both net energy producers and allow nutrients to be recovered while reducing waste sludge production. The anaerobic bioreactor has several advantages, like minimal sludge production due to the low performance of anaerobic biomass, reducing management, stabilization, and final disposal costs, low energy demand, since no aeration is needed for the organic matter degradation, and recovery of energy in the form of methane is possible and can be used to cover the energy of the requirements of the process. However, there are also some limitations. One of them is that the anaerobic biomass presents a slow growth compared to the aerobic biomass, which means that high cell retention times are needed. On the other hand, the high production of wastewater in the per inhabitant in the most developed countries requires low hydraulic retention times, since the treatment flow rates are high. Therefore, large reactors are needed in order to store these high flow rates long enough for the anaerobic biomass growth. What is more, low efficiency in the separation of biomass is another drawback. Physical separation by sedimentation is complex compared to the aerobic treatment, because the anaerobic sludge flocks are smaller and therefore their sedimentation speed is lower. Depending on the configuration of the membranes, we can find three different anaerobic bioreactors. In the tangential flow external membrane configuration, the membrane is attached to the reactor by a pump. This pump operates at high flow rates to reduce the accumulation of solids in the surface of the membrane. The fouling is also prevented with high recirculation rates, which mean high transmembrane pressures and high energy consumption. In the anaerobic bioreactors with submerged membranes, the filtration is performed by generating vacuum in the permeate site, which means lower transmembrane pressure and lower energy consumption. In this case, fouling is prevented with bubbling biogas through the membrane surface. Between this configuration, we have chosen the second one, where the membrane is submerged externally to the reactor because it's easier to clean. As can be seen in this figure, the number of publications from 2000 to 2019 related to anaerobic bioreactor alone and the combination of anaerobic bioreactor and municipal wastewater or sewage waste has continually increased. What is more, in 2009, the publication related to anaerobic bioreactor treatment of municipal wastewater went up suddenly. And in the next decade, this increase was by a factor of 3. However, only from 21 to 30% of the total anaerobic bioreactor publications correspond to the anaerobic treatment of municipal wastewater, which means that this technology is also attractive to other streams like industrial wastewater and solid organic waste. The following table gives an overview of the quality of the effluent and the composition of the biogas and the sludge. As can be seen, the high quality of the effluent means that it can be used for irrigation or fertirrigation. The transforming the methane to hydrogens guarantee the positive carbon footprint. And the membrane technology can be used to concentrate and or recover nutrients for the anaerobic effluents. For instance, hollow fiber membranes contactors is highly selective for nitrogen and phosphorus and can replenish biofertilizer resource. However, there are key challenges that limit the applicability of anaerobic bioreactor technology to municipal wastewater. For instance, municipality wastewater has low COD, dissolved methane loses in the effluent, or the pore size of the membranes are too large to ensure that they retain the viruses, which finally affects overall resource recovery. Among the innovation challenges in SimScience project, we can highlight the digestion of wastewater and municipal solid waste to increase the COD. The pyrolysis of non-recyclable wastes can produce chars that can feed the absorption columns, and methane reforming to hydrogen production. SimScience also proposed two fouling mitigation processes using novel configurations. One of them is to cover the membranes with carbon dots or metal oxide nanoparticles. This configuration will be tested in Denmark, Austria, and Greece. The second one is membrane vibration that will be tested in Spain. Finally, I would like to highlight that the SimScience project is based on the work of 31 partners and represent academic institutions, policymakers, industries from 8 European countries and Israel. If you have any question, you can write to info@simscience.eu, and I will be more than happy to answer you. And that's all from one side.
So thank you very much, Emma, for your presentation and this some examples provided about how the anaerobic membrane bioreactor can be used for the production of different streams from different gas that can be used for new applications. So now we are going to present the last presentation. Now we are going to focus on how we can recover another type of pollutants from water, how this kind of pollutants can also be used for treating again this kind of water. In this case, we are talking about metal brines, and metal valorization for the synthesis and the generation of metal-based coagulants for treating wastewater. This presentation is going to be released by Laura Grima from IDIME. I think Laura is also present here. I don't know if Laura can hear me.
Hi, we are
Hello,
having
Laura.
some software. Hi, good morning. We are having some issues with the computer. Can you give me 2 minutes, please, to share the screen?
Okay, don't worry. If you're still experiencing some issues, I can share the presentation for you. In the meanwhile, Laura from IDIME is trying to solve these technical issues. I want to remember all you that you can share your questions or by chat or raising your hand at the end of her presentation in order to release your questions.
Puedes compartir tú lo de la presentación. ¿Puedes compartir el PowerPoint? ¿En compartir a lo mejor? Está el micro abierto, ¿verdad? Can you hear me?
Hello, Laura. Yeah.
Perfect. Now we are going to try to share the screen. with the
Okay.
presentation?
No problem. If at the end,
Sorry for this. No,
if
it
at
is
the end it's
sharing.
not possible from your side, we can share. But I am already
Okay.
watching the
You're
presentation,
seeing.
and now is in full screen. It's okay.
Oh my God! Thank you. Thank you so much.
Thank you,
Hi.
Laura. No problem.
Thank you. Well, as you have said, I'm going to present the brine and metal waste valorization to produce coagulants for wastewater treatment. First, we will see the problem to solve, the context of the project, then the solution that we have proposed in the LIFE waste to coag. Then we will review the technical concepts of this solution. And finally, we will cover the results and the demo plant of this project. First, let me introduce you the partners of the project. We are 5 companies from different parts of Europe. Global Omnium is the coordinator of the project, and he is responsible of the validation of the technology in the urban wastewater treatment plant. Joviar and Aquafin lead the replicability and transferability of the technology, and IL does the dissemination and communication activities. And from IDME, we are responsible of the technical part. We are doing the design and operation of the demo plant, as well as the environmental and socioeconomic study. The project, as you can see, is expected to finish by the end of the next year. Okay, first, the problem to solve in this project. There are 3 main issues that we are going to approach in this project. The first one, we have the brines. As you know, there is a high generation of brines, both coming from the industrial sector and from desalination plants, being the desalination plants over 100 million cubic meter per day worldwide, which are normally not treated, so they are discharged without treatment. This is cause a harmful environmental impact because normally these brines increase the salinity of the ecosystems where they are discharged. Secondly, we have the metals, the scrap metals. As you know, there is a global scarcity of resources, which combined to the political instability results in an increase of prices of these metals. As you can see in the graph below, we have the evolution of the aluminium prices. This first increase was caused during the pandemics, and this peak was when the Ukrainian war started. So it would be very interesting if we can recover as much aluminium as we can. Finally, the coagulant is not a waste, but they are reagents for the wastewater treatment plants. There is a high consumption of coagulants worldwide, used both in urban and industrial water treatment plants. They are normally outsourced and with continuous price increments. Both the price and the demand of the coagulants is expected to increase because of the stringent requirements in the effluent concentrations of the water treatment plants. So the key of this project is to valorize these 2 wastes, the brines and the metals, into reagents, which are the coagulants for the wastewater treatment plants. But how do we transform these brines and the scrap metals into the coagulants for the water treatment plants? Using the electrolysis. Okay, the solution of this project is based on the electrolysis, in which we apply a continuous electrical current to 2 metal electrodes, which are immersed in a solution to cause a non-spontaneous chemical reaction. Okay, depending on the metal that we use as the anode, which is the sacrificial electrode, we will produce different types of coagulants. If we use steel metal, we will produce the chloride ion coagulants. If we use the aluminum metals, we will produce the substitutes of commercial pack coagulants. Okay. One of the key benefits of our technology is that we are using brines as substitute of the electrolytes. The brines have a higher conductivity, so it allows the application of lower voltages. That means that we have a lower electrical consumption compared to conventional electrolysis. Then this project, we are considering this project a multi-sector approach because all the different streams of the project belongs to different sectors. As you know, our objective is to produce high quality coagulants for wastewater treatment plants, both industrial and urban water treatment plants. And for that, we are using brines that are coming from industrial plants and desalination plants. And also, we are using scrap metals coming from the metal industry. Again, all this process is done through the electrolytic system, this transformation. And this is not the same, because a lot of people confuse it, this is not the same as the electrocoagulation. Okay, now we are going to explain why. Okay, as most of you know, coagulation is a wastewater treatment where the polluting particles are destabilized so they can settle and they can be removed from water. Okay, the conventional coagulation does this by the addition of reagents, normally iron and aluminum salts. And in the electrocoagulation, we use the electric current to generate the active species for this coagulation. This means that in here, the coagulants are generated in situ in this second process. But what is the difference between this electrocoagulation and the system that has been developed in the waste-to-coag process? Okay, it's summarized in this huge table. Okay, we can see first the differences, then the similarities, and the advantages of our process. First, the conventional electrocoagulation, the objective is to treat wastewater, when in our case in the LIFE, we want to produce coagulant and valorize wastes, within this case, the metal scraps and the brines, as we have said before. The electrodes in the electrocoagulation are commercial electrodes, while in the LIFE electrolytic system, we are using metal scraps, which are cheaper and is good for the environment because we are valorizing waste. Okay? The electrolyte in the electrocoagulation is the wastewater that you want to treat, while in our case, we are using the brines coming both from industrial and desalination plants, which have a high conductivity, and as we have said, the higher conductivity, the lower power consumption. And this is also good for the environment, not only because of the power consumption, but because we are treating some brines that are normally not treated. Then, as the similarities of both technologies, we have that both of them are really easy to operate because in both cases, the reaction can be controlled using a power source. That means that you can adjust the coagulant formation depending on how you set the power source, okay? Then in none of them, you don't need reagents to control the pH. This implies that in none of them you use acids or base, which normally is unsafe, and they normally generate more sludge. So both in the electrocoagulation and in our electrolytic system, we are generating less sludge, which is preferred for the water treatment plants. As the advantages of our technology, we have that we are producing a commercial coagulant that you can both sell or use in your water treatment plant, both with the iron and the aluminum coagulants. In our case, we're also valorizing waste, both the metal scraps and the brines, and also, again, thanks to the higher conductivity of the brines, we have a lower power consumption, especially compared to the electrocoagulation systems that are normally used in the water treatment plants. Finally, we would like to show you the pilot plant. And here is the screen from which we control the whole process with the reactors and the deposits of the brines and the coagulants. Then we have the rectifiers from which we control the process. The reactor, that is a filter press configuration and which has almost 1 cubic meter capacity. And as you can see, everything is set up in a container, so it can be easily transferred during all the transferability activities in the different demo sites. We have 3 different demo sites to demonstrate this process, and we are moving it from this container. Finally, We would like to show you some pictures of the coagulants that we have produced. On the left picture is the iron coagulants, and in the right picture we have the aluminum coagulants. And in the left we have the VIP visitor that came once the Dragon plant to the reactor, and we wanted to show you as well. As the conclusions, we have seen the problems covered in this project, which are the brine generation, the metals consumption, and the coagulant consumption. How are we valorizing both the brines and the metals into these coagulant reagents for the water treatment plants through the electrolytic system that we have developed in the consortium. Finally, we have shown you the coagulant production, both with the iron and the aluminum metals. And well, thank you for listening, and I hope that this content was interesting and useful. I'm sorry for the beginning, but this was it. If you have any questions, please feel free to ask.
Yeah, for sure. We have a couple of minutes for questions from the audience. So if you have any question to share with the speakers, please raise your hand. I will give some seconds to allow you to think about the questions. And if no questions are coming from the audience, anyway, if no questions are coming from the audience, remember you have the chat of the webinar that will remain active after the end of the presentation. So as we are very close on time regarding the end of the presentation, I would like to thank again to all the speakers that are participating in the project. Thank you to all the projects, also the coordinators of the projects, and thank you to the audience attending the seminar that I wish has reached the main goals we expect for them. Sharing of knowledge about water treatment, about what the industry, the academia, researching entities and companies are developing now for facing some water problems. And so also thank you very much to the LIFE program and European Commission regarding the organization of the EUGreenWeek partner events. And so have a nice day to all of you. And see you.
Bye.
Thank you, Oscar.
Thank you. Bye.
Thank you. Bye.
Have a nice day.
Bye.